This is a pre-built version of the application. So let's go ahead and run it. So the framework can use cities data coming from three places, either hard-coded or from database or from file. And we will go over how to add, modify, or remove cities data in all three places. And each city is identified by its latitude and longitude coordinates. So here we have hard-coded cities, and here we have cities coming from file and from database. For example, this is the script that creates the European cities, and this one for the US cities. And we are using the Haversine formula in order to calculate distances between cities. So in each route, we start a trip from one of the cities and then go through each city once and then return to the originating city. So let's try maybe using the hard-coded data first. So we have 8 cities here, and maybe let's use the brute force algorithm to find the shortest route. And we are running in default mode, so we did not show all the permutations, and all of those routes are equivalent. So if we start from here, from Houston, Austin, LA, it's the same as here: Houston, Austin, LA, San Francisco, Denver, Chicago, and then going back to Boston. And we can go the other way around. So Houston, New York, Boston, and then going to Chicago, Denver, etc. So this is the shortest distance that we found in miles. And we found the shortest route after this number of permutations. So since we have 8 cities, we have 8 factorial permutations. And we can do the same thing except run in verbose mode. So let's use verbose. And still use hard-coded data and do brute force. So we're showing all the permutations, and same thing, we got this distance in miles after 8 factorial permutations. So this is 8 factorial. So we started with this, the first permutation, and actually we started with this one as the first permutation, and it has this distance in miles. So we considered it as the shortest distance, and then we went to the next permutation, and it has this distance, which is shorter than this one. So now this one is the shortest distance. And same thing, we went to the third permutation. It's bigger, so we still have this one as the shortest permutation. And we kept going until here. This is, no, actually this is bigger than this. So we kept going until here. So this route has this distance in miles. So now we considered it as the shortest distance. Then this one is bigger, so this is still the shortest, and we kept going. So we couldn't find any distance shorter than this. And this was the last permutation. And we ended up with those permutations, having the shortest distance, which are all equivalent. And I want to pick up the data from database. And I want to show how we change the database. So maybe let's make some changes to this. So let's go to this script that creates the European cities. And maybe remove those two and add those two. And run it. Actually, let's stop the application and run the script. So any one of those three scripts can create this database. So let's delete it. And that database will have European cities. So here we go. This is the database. And now if we run the application, we have this different route with those two changed cities. So we'll run in default mode and pick up the data from the database. And same thing to brute force. So this is the shortest distance in miles that we found, and all of those are equivalent. And this is 9 factorial permutations. And let's pick up data from file. So we have how many? 9 cities. So we should do the same number of permutations. So pick up from file and do brute force. So same number of permutations. and this is the shortest distance that we found, and all of those are equivalent. Now brute force becomes much more time consuming the more cities we add to the route, since we end up with much more permutations. That is why for a large number of cities, that brute force way of finding the shortest routes become impractical, since the number of permutations increases significantly. And this is why it makes sense to use other algorithms than brute force for a huge number of cities. And I also wanted to mention for files, those are for convenience, so we can put any cities here, copy them from any one of those files. You can add your own here. Also, you can add your own script here to create any cities, any collection of cities or set of cities that you want to put in the database. Next, let's try finding the shortest route using genetic algorithm, and maybe use data coming from the database and do it in verbose mode. And we are sorting by fitness, so the highest fitness means the shortest distance. So we found this route as the shortest route after 30 generations, and it has this total distance. And each generation have 8 routes, and we specify that here, so the population size, and we specify other things here, that we are doing 30 generations. So after 30 generations, and the number of elite routes that stay the same from one generation to the next. So we started with this as the shortest route in this generation, and we evolved from one generation to the next using selection, crossover, mutation, and elitism, and we ended up with this as the shortest route. So let's do the same thing, but use maybe nearest neighbors. So we started with this as the initial route, having this distance in miles, and we ended with this having this distance in miles. So we randomly picked this city from here, and those are the remaining cities. And we checked which one of those remaining cities have the shortest distance to the picked city, and it turned out this one does have that shortest distance, and those are the remaining cities now. So we tried to find which one of those remaining city has the shortest distance to Paris, and it turned out that this city does. So now those are the remaining cities, and same thing, this one has the shortest distance to London, and those are the remaining cities. We keep doing that until we don't have any remaining cities, and we end up with this as the shortest route, having this distance in miles. And let's do the same thing, but use ant colony optimization. So we used 500 artificial ants, and this ant found this distance in miles, ant number 1, and this other ant found this distance, and this one, ant number 152, found this one, and this ant found this one. So we found this shortest distance with this shortest route with this total distance. And let's try using hill climbing. So we started with this route, having this distance in miles. We compared it to the adjacent route, and it has a shorter or equal distance, so we proceeded. So it has this distance. So now we are here, and the difference between those two, that we have Rome and Amsterdam flipped. So here we checked the adjacent route, and it has a shorter distance, so we proceeded. So now we are here, and we checked the adjacent route, and it has a bigger distance, so we stayed. And here we are the same as here. So we checked the adjacent route, it has a shorter distance, so we proceeded. So now we are here, and this one has a shorter distance, so we proceeded. So now we are here, and we kept trying and found a larger adjacent route, so we stayed for 9 iterations. And then here we found that the adjacent route has a shorter distance, so we proceeded, and we kept doing this until here we did 9 or 100 iterations, and we set that here, so iteration before maximum. So we consider this as the shortest route, so a potential maximum. So we found this route having this total distance in miles. And let's try what remains is using simulated annealing. So let's do that. So we found this route having this total distance in miles. So with simulated annealing, the idea is as the temperature is very high, it's very easy to make changes, but as the temperature decreases until here, it is this one, it becomes harder and harder until it becomes no longer possible to make any changes. So to achieve that, we use this probability function with the new temperature equaling the old temperature times 1 minus the rate of cooling. And we are using this as the rate of cooling. So here, this route has this distance in miles, and we check the adjacent route and it has a shorter distance, and the difference between those two is that those two cities are flipped. So we proceeded, and now we are here, and we check the adjacent route, and it has a bigger distance. So we check the random number if it is bigger than the probability function, and it is, so we stay. So here we have the same route, and same thing, we checked the adjacent route and it has a bigger distance, so we check the random number and it is bigger than the probability function, so we still stay. And now we are here, and this one has a shorter adjacent route, so we proceed, and now we are here, and same thing. Actually, this one has a larger distance, so we check the random number if it is smaller or equal to the probability function, and it is, so we still proceed even though this is larger than this. So now we are here. So this is the difference between simulated annealing and hill climbing. So now same thing, the adjacent route has a bigger distance, but we still proceed since the random number is bigger, is smaller or equal to the probability function. And here we stay, since the random number is bigger than the probability function and the adjacent route has longer distance. So now we are the same here, and we check the adjacent route and it has a bigger distance, but we still proceed since the random number is smaller or equal to the probability function, etc. We keep doing this until we end up with this as the shortest route. And while we're doing this, the temperature keeps decreasing. And this source code will be available for download. Also a longer version that includes the coding and test running of the application will be available for viewing by channel members at the senior developer level and above.